Saxon Advanced Mathematics, Lesson 7. Greetings, my students. The topic today is logic. Okay, before I go any further, I'm going to tell you in a very practical sense that this lesson is kind of a quirky little magic trick of a lesson. We're going to talk about this. We're never going to talk about it again. We're not going to build on this in any way. Logic is a branch of mathematics, and John wants to expose you to it so that you have an idea what it's all about. It is part of mathematics. It's called non-quantitative mathematics. I'm not writing any of this down because I don't want you to even worry about it. There is a logic class at Edmonds Community College that can be used to meet, it can be used as a mathematics class. I think all of my daughters took it, but they really enjoyed it. If you have a math brain, it's a kind of a fun thing to play around with because you use words instead of numbers. In fact, one of my daughters, the professor there, who they loved, he was there for a long time. I don't know if he's still there. My daughters were at Edmonds Community College in the late noughts and the early 2010s. He tried to convince one of my daughters to become a logic major, and she politely declined and studied painting and drawing instead. But anyway, it's kind of cool. It's a great class if you're ever looking for a class to take there. So we're going to plow through this and have a little fun with it. I think you guys will find it somewhat, dare I say it, logical, but don't worry too much about it because this is just kind of a fun little side note that we're exploring only today. Inductive reasoning. Inductive reasoning is a type of thought when you're trying to find a rule. We do it a lot in mathematics. Deductive reasoning I spelled that wrong. Reasoning is the process of using an established rule. All right, so they're subtly different, but they are related. These are the pioneers that go first and find the rules, and then we're the ones who follow along. The Greeks did a lot of the heavy lifting for us here. Another reason that we want to talk about logic is because logic underpins geometry and algebra. Again, the early mathematicians and geometrists went ahead and found rules for us, and we now use their rules to move ahead. Okay. I'm trying to just edit out as much of this as possible. I want you to hear the words though. The ancient Greeks studied reasoning, these two forms of it, using what are called syllogisms. A syllogism is a process that we're going to use in which you have a major premise, and I'll give you an example in a minute and you'll be like, oh, okay, that makes sense. A minor premise, and then you use those to reach a conclusion. And we very often draw a line right here. It's almost like a addition or subtraction problem, okay? Here's an example, and I'm just gonna look at the book. And I wanna choose the easiest one first, right here. All frogs, you can't read that. Or you'll have to squint to read it. All frogs are green. Okay, that's our major premise. It's a broader, more globalized statement. Okay, so that's the major premise. Again, it's a broader, it's a general rule. Henry is a frog. That is called the minor premise, and you can see it's more specific. It's a statement. Now we draw our conclusion, and John has drawn the conclusion that Henry must be green. Now, we're not necessarily testing the reality of whether Henry really is a fraud. We're not testing whether this is absurd or not. We're simply saying if this is the major premise and this is the minor premise, is the conclusion valid or invalid? Not true or false, but valid or invalid. So it can be nutty, but it's just a question of whether these two premises lead us to a valid conclusion. Okay, so in this one, we're talking about the group of frogs. And we're saying that a condition of all frogs is that they are green. We're saying that Henry is a member of this group. So therefore, he must be green, and that is a valid conclusion. Okay? So it is sound from the point of view of logical reasoning. Okay, let's look at one with an invalid conclusion. The major premise: if it rains, I will go to town. Now, we might sit here and think that's dumb. If it rains, you should stay home. That's not the point. We're given this major premise as a general rule. The minor premise is more specific. It did not rain. So let's follow again the way we did last time. The major premise describes the general rule. That's the condition. We look to see if the minor premise meets that condition. Let me show you the ending thing. If it rains, I will go to town. But we're saying it did not rain. We're saying that our minor premise does not meet the qualifications of the major. Remember, before it was the opposite. Henry is a frog, and we were talking about all frogs. We're talking about situations where it's raining. It did not rain. So this major premise doesn't have anything to do with our particular condition, because our condition doesn't meet the condition of the major premise. So this is invalid. It might be perfectly true. It might make common sense to not go to town, but it's not a valid conclusion from these two premises. Try a few more. Excuse me, my pages are all rumpled and I can't have that. All right, is the following argument a valid argument? Why or why not? All normal dogs have 4 legs. Okay, so this is a statement about normal dogs. That dog has 4 legs. And we're testing the conclusion, therefore, that dog is normal. There is a normal dog. Okay? Major, minor, and conclusion that we're determining whether it's valid or invalid. The group that we're describing is all normal dogs. The specific dog that we're talking about does not fit this category, so we can't make a conclusion about whether it's normal or not. It has 4 legs. It meets this characteristic, but it has to meet this characteristic in order for it to be valid. So this is an invalid conclusion, because our minor premise does not fit with the major premise. Let's try another one. These are the examples, by the way. This is 7.1. This is example 7.2. All boys are good. That child is a good child. Okay, major premise, minor premise. And we already see a problem because the major premise is about all boys, and we're not told anything about whether this child is a boy. Therefore, that child is a boy. And we can see that this one is invalid because the statement is about all boys. The minor premise does not state whether or not it's about the boys. Again, it's focusing on the latter part of the major premise, but not the descriptor of it. So this is also invalid. Wah, wah. Again, these can be somewhat absurd, but we're not testing whether they make sense, whether they're true or realistic. We're simply testing whether the major premise supports, or whether the minor premise fits with the major premise. This could obviously be a girl that's a good girl. All boys are good, but it doesn't mean that all girls aren't good too. So this could be a good girl and not necessarily a boy. This one with the dogs, all normal dogs have 4 legs. That dog has 4 legs. Well, yeah, maybe it has 4 legs, but no head. I mean, again, we don't have to be logical, but we can easily imagine a scenario that disproves the minor premise. Let's try this one. This is the last one of these. Example 7.3. All chickens have 3 legs. What did I just say? Yeah, I said it right. All chickens have 3 legs. I said that right. Henny Penny is a chicken. All right, there's our major and our minor. And we can see this one feels good because the major premise describes all chickens, and we see that Henny Penny fits that category. Okay, that's what we like to see. Let's see what the conclusion is. Henny Penny has 3 legs. And that sounds right, right? All chickens have 3 legs. Henny Penny is a chicken, so she fits this group, so this condition must extend to her as well. So that is valid. Kooky, because chickens with 3 legs, that makes no sense. But again, we're letting go of that. We're simply talking about the accuracy of the syllogism. And remember, that's what these little situations are called with the minor premise, major, minor, and conclusion. That's called a syllogism. Okay. Now, we're going to take this same idea and state our premises in slightly different language. And there's some fancy words that go with this. I want to just show you how it works before I introduce all the fancy words. All right. We're going to take another one of these syllogisms, just like we did. All non-athletes are vegetarians. I ran out of room. All non-athletes, that's the group we're talking about, are vegetarians. Jim is a non-vegetarian. That's our minor premise. All right, we can see there's a problem here right away. Because he doesn't fit this group, so we can't draw a conclusion about him. Let's see what the conclusion is. Therefore, Jim is an athlete. Okay, this is the way we looked at these before, and what we're going to do is we're going to restate this using a situation, a technique called the contrapositive. it's sometimes easier to understand if we write the premise in an if-then form. So we're going to take this major premise and we're going to restate it as an if-then. Here's the way that would look. If non-athlete, then vegetarian. Whoops, I forgot the N. See, I took the major premise and I just restated it into an if-then format. If non-athlete, then vegetarian. Okay? And we know that Jim is a non-vegetarian. Okay, and we see that these don't match, right? So what we're going to, because we're talking about non-athletes, but we want to be talking about non-vegetarians. So what we can do is we can replace the premise with its contrapositive. That's the fancy word. And what we do with that is we state kind of the opposite of this. And if this, we say if non-vegetarian, then athlete. Do you see what we did? I'm getting sunshiny. Let me scoot down. We switched the negatives. If non-athlete, then vegetarian. We wrote the contrapositive. If non-vegetarian, then athlete. Does that make sense? We flipped it around. Now the conclusion that we've been trying to draw is that Jim is an athlete. In this situation, it doesn't look like we have proof to make that valid, but when we use it this way, if non-vegetarian, then athlete, Jim is non-vegetarian. So by using the contrapositive, we can state this in a way that creates a valid argument. The conclusion is not necessarily true, right? Is it really true that if you're not vegetarian, then that means you're an athlete? Not necessarily. I'm a non-vegetarian, but I don't think I would call myself an athlete. An outdoors woman, perhaps, but not an athlete. So this isn't necessarily true, but the argument is valid according to the rules of logic. That's what we're examining here, is the rules of logic. So a contrapositive is created when we write our major premise in an if-then format and swap the meaning of the format. We switch the nouns and, right, if non-athlete, then vegetarian, we slipped it to if non-vegetarian. So we made that the negative and we put it first, and we took the negative off that one and put it second. So you flip them, which is weird. I completely agree. And then here's just another way to note some of this. We're almost done with this lesson. The last one, we're just going to do an abbreviated form of this, and we're talking about converse and inverse. Don't let those words distract you for the moment. Let's look at two simple premises in abbreviated form. If normal dog, John always, no, he doesn't, then 4 legs. We talked about that one before. And here's another one. If rabbit, then fast. All right. We can generalize both of these premises by using P for the P equals the if part, Q equals the then part, and we put an arrow in between them. Okay? So it would look like this. This is an abbreviation for if something, then something. Okay? If P, then Q. This is what we call a premise, right? This is a shorthand version of what we were doing up here. Now, what we can do is write what we call the contrapositive. And it goes like this. Whoops. If it doesn't have 4 legs, then it's not a normal dog. If it's not fast, then it's not a rabbit, right? So by negating them and flipping their order, we can create what's called the contrapositive. There are 2 other ways that logistics write things, and that is called the other way statement of the premise, which is called the converse. Okay, so we've already talked about this one. We've already talked about this one with Jim and the athlete, talking about how you can reverse them. Now we're talking about sometimes the converse is true, which is called the other way. And in this case, it would be, if it's fast, then it's a rabbit. If it has 4 legs, then it's a dog. And often we'll say that, blah, blah, blah is a fact. If it's a normal dog, then it has 4 legs. But the converse is not true. Sometimes we'll say that because we're ruling it out. But the converse is the idea that we flip the if-then part. So this would be, if it has 4 legs, then it's a normal dog. If it's fast, then it's a rabbit. The other one is the inverse, in which we take the original premise and we make both of them negative and see if it's true. If it's not a normal dog, then it doesn't have 4 legs. If it's not a rabbit, then it isn't fast. And oftentimes this leads to problems in logic because we assume if the premise is true, we often try to assume that the converse is true and that the inverse is true, but these are often not true, right? If a normal dog has 4 legs, then anything with 4 legs is not a normal dog. You can't reverse them. So these are important ideas because they create different meaning from our original premise. That's all I want to say about it. I don't want to get into it. There's one last little idea John explores, but I don't want to get into it. So what we have to do is be careful when we're talking about a premise, as we do in geometry, and we'll talk about that. Just because the premise is true, we can't always change things around, right, and flip it. I don't want to get into specific details, but we have to be careful when we're doing geometry that we use the ideas as a premise, but be careful if we try to break it around. Oh, so I'll give you an example. If it's a square, then it has 4 equal sides. Okay, is the converse true? Let's see. The converse would be if 4 equal sides, than a square. That's not true. Because it could be a rhombus, right? It could be like a diamond, and all the sides could be equal shapes, but that's not a square. So the converse fails. What about the inverse? Would the inverse be true if not square? Then not 4 equal sides? No, that's not true either, because if it's not a square, it could be a rhombus and then it would have 4 equal sides. So just because the premise is true doesn't mean that the converse or the inverse are necessarily true. And I bet if I thought for a minute, I could think of one where the premise is true and maybe one of these but not the other would be true. None comes to my mind immediately, and that's okay. But the idea here is that we have to be careful when we take a premise that we understand exactly the if-then nature of it, and we don't flip it around and try and apply it in the other way, and we don't assume that the negative is true. Okay, in the homework, you're going to just have a few of these. Do not sweat it, you guys. Just have fun with this, and check out that logic class if you're ever interested, because it's kind of fun once you get into it. This was a little confusing because we're literally talking about it for what, 20 minutes, and that's all. But if you spent a semester exploring these ideas, you would probably find it really cool and really fun. So that's all I have to say about logic. Thank you and goodbye.